Hi, good morning, students. So then in the last class we discussed about circuit analysis. Actually we started there, an application of Kirchhoff Law for this capacitive circuits, and then we discussed about like Weisstrom bridge with the capacitive circuits, and we also discussed about combination of capacitors and resistors, right? And so now let us see some other applications of this, some other problems or other models based on this finding the effective capacitance or charge on different capacitor or potential difference across different points. You can do different calculations regarding this circuits here. So now I am taking that one such a problem here. Just I will explain how to apply this perpendicular symmetry, parallel symmetry, or this shifted symmetry or path symmetry for different types of the circuits here. Just I am taking a simple problem here. So let us take the capacitors or different capacitors or connected like this. So that here all the, let us take identical capacitors or connected here, so that this effective capacitance is equal to that of C. That means equal, each capacitance is C. Suppose we need to find this effective capacitance between these 2 points A and B. So all are identical capacitors only. So effective capacitance between those 2 points we need to find here. So you can apply either, you can discuss either based on the parallel symmetry you can apply, because such a problem we solved already for the resistors, right? So you can apply either parallel symmetry you can apply, or perpendicular symmetry you can apply here. So simply if you are applying that perpendicular symmetry, then perpendicular symmetry means then here we need to assume like a charge is entering here and charge is leaving at the point B here, right? So charge is entering at the point A and charge is leaving at the point B. So that means you can say charge is flowing along this direction. So when the charge is flowing along this direction, then about this axis, so you can consider like this is some XY axis you may consider here, or you may consider this PQ axis. So then about this PQ axis, the circuit is symmetrical. So when the circuit is symmetrical, then you can say that all the points lying on that point on that circuit will be, that means on that line will be at equipotential. So you can remove those capacitors here, because that means you can join them. So this point and this point, let center is O here, then this point P and O will be having same potential, and O and Q will be having the same potential here. So that means now, so what we can write here is about axis PQ, the circuit is symmetrical. Right? So the circuit is symmetrical, and so that that means now it is a perpendicular symmetry, as we know, and perpendicular symmetry means all those points will be at same potential here. Therefore we can write here it as Vp is equal to V naught is equal to Vq. Those points will be at same potential, we can write here. So and when those points are at same potential, then you can observe this, there is no charge storing on this capacitor here, right? So when there is no charge on this capacitor, then you can remove that capacitor. Similarly here you can also remove this capacitor here. Then the remaining circuit you can simply draw like this. So then the resulting circuit will look like this. So then only this this rows will be there here. That means these capacitors, and similarly here this combination will be there here. Right? If you remove that, now see that how simple that circuit is. Now only series and parallel combinations are there here, right? So that means these 2 capacitors are in series, these 2 capacitors are in series, and those 2 capacitors are in series. So then all those 3 are in parallel. So series means C by 2 you will get. So C by 2, C by 2 and C by 2, all those are in parallel. Therefore I can write this C effective directly, we can write this as so 3C by 2, right? So then that is the effective capacitance for this given circuit here. So like that you can solve easily as we completed this circuit analysis for the resistors here. So that is the advantage why I am saying this capacitors topic now. And so next, similarly, suppose you may consider this another example like and suppose I am taking this another example here. So just let us check this problem here, like suppose so then again another square you can draw here, like another, this is another point here, this from this another capacitor will be there like this. So from this point this circuits will be there like this. So now this is another circuit, let us take another example like this, and here also let us take all the capacitors or identical I am taking here. This is the point A and this is the point B. So between these 2 points we need to find this effective capacitance. All are identical only. So all are identical. So each capacitance is C. Right? And so now the effective capacitance we need to calculate. Find effective capacitance between A and B. So then here also now we can observe that by using perpendicular symmetry, now you can observe this. Again you can consider this about this axis, then circuit is symmetrical. Right side and left side are symmetrical only. And so right side and left side is symmetrical in the sense what you can write here is again all the points lying on this line will be at same potential. So you can remove this, that means this point and this point will be at same potential, and this point and this point will be at same potential. So again you can remove this capacitor here. That means now this capacitor you can remove here, and this capacitor also you can remove here, right? And so by removing those capacitors, now we can easily solve that circuit. Once that those capacitors are removed, then you can observe that these two will be in series and these two will be in series, and so then that combination will be in parallel. So you can simplify that easily. So then these two will be in series and these two will be in series, and so I can draw this circuit like this. The resulting circuit looks like I am drawing its value here. These two are in series, C by 2 and C by 2 you will get, and this will be C by 2, C by 2, both are in parallel, so C you will get. So finally what I can write here is, so here it is C, C and C, 3 capacitors will be there here, and this is another capacitors will be there like this, that you can redraw the circuit like this. So then this capacitance is C by 2 and this is C by 2. And this is C, C and C. So is it clear? So that means these two capacitors C by 2 you will get, so that is here, and these two capacitors C by 2, that is here. And now for this square you will get another capacitance C here, the equivalent of that square, and so this is the remaining two C's are there here, so that just I am representing like that. So then you can simplify this effective capacitance there. So then effective capacitance I can write here it as C by 2 plus here you will get C by 3 plus C by 2, right? And so which is nothing but 4C by 3 we can write. So it is effective capacitance of that combination there. So then like that you can apply this symmetry methods easily for this. And then suppose I am taking another example like let us take another example for this. And removing the junctions we discussed there, right? So let us see one such a problem here by removing this one of the junction there. That means now I am taking the circuit like this. So then here from this point so that means here it is like this. This is one capacitor will be there like this, and another capacitor is there here, and from this you can draw this two capacitors are connected to this point like this, right? So in resistors we solved already this type of problem again. So So then effective capacitance again we need to calculate here. All are identical capacitors here. So then all are identical, then effective capacitance we need to find here. So all the capacitors are identical. Find effective capacitance between like A and B. Effective capacitance between A and B. So you know already like in resistors, in different ways we can solve this circuit here. Out of them, in resistors we solved by different methods. I explained by like symmetry method, perpendicular symmetry I explained, and by removing the junction I explained, and finally at the last of the circuit analysis we also discussed delta star method. So by using the delta star method also you can solve the circuit. But instead of all these methods, the simplest way is by removing the circuit here. So that means by removing the junction. So that means here how to remove the junction means, again here you can observe that suppose I am taking this Q1 is the charge flowing along this direction here, and Q2 is the charge flowing along this direction here. When entering and leaving junctions are identical, then same amount of charge will come out of the circuit along the identical paths here. So that means now this path and this path is identical. So along this direction the same Q2 should come along this direction here. And now this path and this path are identical. So along this direction the same Q1 should come out of this here. And so that then that is nothing but what equivalently is we can say that here there is no any division of this current here, division of the charge. And so that what we can say is we can remove this junction here. We can remove that junction. Or you can say that in terms of charge isolation, then only charge on these two capacitors will become 0 without adding these charges on these capacitors here. So we can remove that junction there. So once that junction is removed, then the circuit will look like so then this is our equivalent circuit then. Once if that junction is removed there, so then this is our combinations here, right? So this is our A and B. So now this is C, C, and this is another C here, C, and this is C. Just we are removing this junction here. So once that junction is removed, then you can solve that capacitance easily. These two are in effective capacitance easily. These two are in series, C by 2 you will get, that will be in parallel with this. So C plus C by 2, 3C by 2 you will get, that 3C by 2 is in series with this 2, and that is finally in parallel with this combination here. So find the effective capacitance or simplify this further calculation here, right? Is it clear? These two are in series, C by 2 you will get, that C by 2 is in parallel with this. So C plus C by 2 means 3C by 2 you will get, and that 3C by 2 is in series with this combination here. So that means now, so then there the circuit will be, you can represent like this finally here. So then these are our A and B points here. This is C by 2, the resultant of these two, and this is 3C by 2, the resultant of these 3. And so now here next C and C will be there here, right? And so then simplify that effective capacitance there. So I can write this first these two, then those two you can say that C by 2 you will get, or otherwise you can write like 1 by C dash is equal to 1 by C plus 1 by C plus 2 by 3C. The resultant of only these three I am finding there. So therefore this 1 by C dash is equal to, you can write this as 3C, and then take LCM there. So 3 plus 3 plus 2. Therefore this C dash is equal to 3C by 8. So it is the effective capacitance of those three capacitors. Now that combination is in parallel with C by 2. Therefore finally this C effective value we can write it as 3C by 8 plus C by 2. So which is nothing but 7 by 8 C. I think in resistors also we got such a similar value, 7 by 8 or I think. So then that is our value there. Then if all are identical, if you are taking all of them as identical. And so then that is our effective capacitance calculations just by removing this circuit here, right? Then I will give some problems based on this, and so solve by using this symmetry methods, right? So now let us solve these problems here. Just I am giving 3 problems, but in this these problems in resistors you already solved these problems here. So that means in this we need to find across body diagonal and face diagonal and adjacent sides. That means here you need to find effective resistance, effective capacitance between A and H junctions and between A and C junctions and between A and B junctions. So means across those all those values we solve for the resistors. So just apply the similar principles and then solve that effective capacitance. Then similarly for this it's a base is a square and then it's a pyramid arrangement is there here, and for this also find the effective capacitance between like A and O, right? This is effective capacitance between A and O, and then you need to find another value as effective capacitance between A and D. So find the effective capacitance between those. You can apply either of our techniques, path symmetry or removing the junctions in and especially this problem, removing this junction we can apply here for if you are finding this AD. So once you go through that resistor problems and remember revise those problems, and once you solve this so that you will get the circuit analysis both in resistors and capacitors. And similarly here this is the base of this base here, ABC is the base of the triangle, and from 3 vertex and 3 capacitors are joined at the point O here. Then we need to find the effective capacitance between A and B. So find the effective capacitance between A and B. So then solve this, practice these problems here, so we will get a better idea about that. That means this path difference, path symmetry problems are already included in this. That means if you are taking either this problem or this problem, C to H problem, then we solved resistors by using path symmetry one, right? And so then those problems are already included in that. And next here let us consider in case of like shifted symmetry, one more problem we solved there. That means Wheatstone bit G is, if Wheatstone bit G is not balanced, then how to solve that. So let us see that. So if Wheatstone bit G is not balanced and it is like a shifted symmetry, then we can solve these circuits like this. So I am taking one circuit here. So I am taking the circuit like this, right? So this is our circuit here, A, B, and we need to find the effective capacitance between this A and B when the values are given like this. This is C, 2C, this is 2C and C, and this is 2C. So now it looks like Wheatstone bit, but it is clear that it is not a balanced Wheatstone bit. So right, then in such a case how to solve it? But it appears like if you are interchanging these two capacitors or if you are interchanging these two capacitors, then it will be a balanced Wheatstone bit. So that means then this such a type of circuits are nothing but we call shifted symmetry, right? And so now this problem is related to that shifted symmetry here. So then this is based on this shifted symmetry. So then this shifted symmetry is nothing but like this. When you are interchanging those resistors, if you are interchanging for example these two resistors 2C and C, it becomes a balanced Wheatstone bit. So then such a circuit is nothing but we called like balanced shifted symmetry here. And here generally to solve that, either you can apply that Kirchhoff law here. You can apply the Kirchhoff law to reduce that variable, then we use this shifted symmetry principle here. So that means for this we imagine to apply this Kirchhoff law to find this effective capacitance, we imagine a battery is connected between these two here. So battery of EMF V is connected here, right? And now suppose this battery is supplying a charge Q here. So that means this Q is a charge flowing from this battery, and out of that I am assuming that Q1 is the charge stored on this capacitor here. And so now this Q minus Q1 will be there on this capacitor here, right? And so now the polarities means then this will be positive plate and this is negative, and similarly this is positive and this is negative plate will be there, right? And next similarly for this now our shifted symmetry is now charge on this C and this C will be same, and so that then this is nothing but we consider it as a plus Q1 charge will be there here. So this is plus Q and this is minus Q here, and similarly charge on this will be Q minus Q minus Q1 will be there, so that this is positive and this plate is negative plate here, right? We need to write the charge on this capacitor here. So let us assume that charge is some Q2. Now here the question arises whether you need to take upper plate as positively charged or a lower plate as positively charged for this plate, for this 2C capacitor. Because for this you can decide by using this just by seeing the polarities of this battery here, right? And so now for this, as we know in Kirchhoff law, there is no any confusion regarding the current direction, current flow direction. In any direction you can assume, just finally if our assumption is wrong, you will get the answer with the negative sign. That point we already know that. Similarly here in case of capacitors, in such a cases whenever you are getting such a doubt, you can assume that capacitor charges polarities in any way. Either you may consider upper plate as positive or lower plate as negative, simply will get that answer with the negative sign there. So now suppose I am assuming that upper plate as a positive plate here. Suppose then I am taking this as plus Q2, I am taking here some charge on this, and this is minus Q2 charge, right? And so then that is our first Kirchhoff law here, charge distribution here. So now in this charge distribution, what we can consider here is, I am taking this isolated plates here so that you will get this charge relation. That means just we need to apply this Kirchhoff first law here, right? So then this is the isolated system here. So for that isolated system, let us apply this junction rule here. So I am writing this junction rule now. Let us give some names here. Suppose this is C, junction C, and this is some D. So now by KCL at junction C, either you can apply at C or you can also apply it at D, because here D also for these three plates or isolated plates. So that means either you can apply for this these three plates or you can apply for this lower combination also. You will get the same result finally. And so now I am writing here. So here charge on this plate is minus Q1, clear? And a charge on this plate will be plus of Q minus Q1. The charge on this capacitor, these two charges are same. And a charge on this upper plate is plus Q2. So this value should be equal to 0, right? Net charge at any isolated junction should be equal to 0. So from this you can get an expression for this Q2 here. So therefore this Q2 we can write this as 2Q1 minus Q we can write. Let's suppose this is equation 1. So now our processor is only one variable is there for us now, that is nothing but Q1. So we need to write an expression for Q1 just by applying the Kirchhoff laws. Just by applying Kirchhoff laws we need to write an expression for that. And so now here just I am taking this one of the loop here. So now I am taking this by Kirchhoff voltage law for loop ACDA, and this point here itself I am taking here. Either you can consider here or here, there is no problem because it is just a conducting wire only. So this point I am taking as A. So then for this closed loop I am applying here. That is the meaning of this. And we are applying in this direction here. So let us write the Kirchhoff law now. So then here we are traveling from this positive plate to negative plate. So then it is minus Q1 by C, right? And next here we are traveling from this positive plate to negative plate. So minus Q2 by 2C. And then next we are traveling from negative plate to positive plate here. So negative plate to positive plate means then plus we need to write here. So plus, and there the charge is Q minus Q1 by 2C. So this value should be equal to 0. That means only capacitors are there. So then that is our potential drop in that closed loop here. So now let us simplify that equation. Then you will get one relation here. So by solving equation 1 and equation 2, you will get the expression for this Q. Just I am multiplying with that 2C here. Then minus 2 into Q1 minus Q2. That Q2 value we can write this as 2Q1 minus Q. By using this relation, that Q2 value I am substituting there. And plus Q minus Q1. This value is equal to 0. So let us simplify this equation here. So this is minus 2Q1 minus 2Q1 plus Q plus Q minus Q1. So this is equal to 0. And so now we can find this Q value here. Therefore this 2Q is equal to 5Q1. And therefore this Q1 is equal to, I can write this as 2 by 5Q. Right? So let's suppose this is equation 2. Is it clear? That is our Q2 or Q1 value. Q1 value in terms of this Q. So then after getting these variable values, we know to find the effective resistance or effective capacitance by using Kirchhoff law. Finally, we need to apply this Kirchhoff law by including this cell here. So by including the cell, we need to apply this Kirchhoff law here. So now by applying this, you can follow the any path here. So like either you can consider this path you may consider, or this upper path you may consider, or here you may convert like this, you may come down like this. Any path you can consider, you will get the same answer. So now finally I am writing this by KVL for loop. So I am taking like upper path here A, C, B, A. Right? I am taking this path here, including the cell you should take here. You can internal for the circuit, you can take any point you can consider there, right? So now let us apply here. Minus for this Q1 by C for this capacitor. And next we are moving to here. So then here again we are traveling from positive plate to negative plate. So minus, there the charge is Q minus Q1 by, there the capacitance is 2C. And next we are moving to this here cell. So for the cell we are traveling from negative to positive terminal here. So then this negative to positive terminal means plus V is equal to 0, right? So that is our Kirchhoff law for this closed loop. And so now let us write this equation as V is equal to, so you can simply take an LCM here. So I can write this as Q1 by C plus or 2Q1 by C plus Q minus Q1 you can write. Just we are adding these values here. When you are adding those values, then here this value is 2Q1 you will get if you are taking this LCM, sorry, by 2C you will get here. And then this we are writing this other side here, then this value is plus and this is minus you will get there. So that is our equation there. So then you can simplify this as V is equal to like Q1 plus Q by 2C. Now we can substitute that Q1 value from this equation here. From this equation Q1 is 2 by 5. So let us substitute this value, and this side I can write this as, so let us simplify that. Finally we can substitute this V value here. So then it is 2 by 5Q plus Q by 2C. And therefore this V is equal to what we can write is 7Q by 10C. So but finally what we can write here is V value we can write as Q by C effective we can write here. That means we are replacing this total system by total given circuit by one capacitor whose capacitance is C effective. Then the charges applied, so Q by C effective should be equal to potential difference applied there. Therefore you can write this expression as I can write this as Q by C effective is equal to 7Q by 10C. Therefore this C effective value will be equal to 10C by 7 you can write. So is it clear? That is the effective capacitance of that combination now. So that is our shifted symmetry advantage there. That means by using Kirchhoff law, that is a way to find that capacitance here. So just we need to find the C1, C2 Q1, Q2 expressions in terms of this total charge here. We are assuming the total charge Q is entering the circuit here. And then here some distribution we need to take here. Some variables we need to consider there. Like I1, I2 we consider in resistive circuits. And here similarly, first after taking this current distribution, we need to write the Kirchhoff first law to get the relation between Q1, Q2 and Q3. Whatever the variables we are assuming across among them, to write the relation among them, we need to write this Kirchhoff first law here. So then after that you will get the relations here, some relations between the different charges what we are assuming. So that is a way of writing here. Here I am assuming this total charge on this system will be, isolated system will be 0. So then just I am equating that, then we are getting this one relation. So just by applying Kirchhoff law, we are getting another expression here. So by From this we are getting this Q1 expression as a function of Q. Then by using Kirchhoff law, we know finally we need to apply one more time this Kirchhoff law by including this L here. So finally we write, in case of resistive circuits, we write this I expression as like IR. We write this I expression as IR. Now here we need to write this as Q by C effective, we need to write here. So there we write I into R effective, we write in case of resistive circuits, but here we need to write like this, right? So that is based on this shifted symmetry here. So from this problem we should also understand that how to find effective capacitance by using the Kirchhoff law. So that is a way of finding this effective capacitance by using the Kirchhoff law here. And actually nodal analysis will also be there. And so now let us check by using this, let us apply for the same circuit I will apply the nodal method also. So nodal method means, it is just based on the Kirchhoff first law only, right? Just we write the algebraic sum of all the currents at any junction is 0. And here we need to write algebraic sum of all the charges at any junction is 0. Just write here nodal analysis. Nodal analysis for this capacitive circuits here. So in that again just our procedure is same as that of our resistive circuits here. So our procedure is same as that of our resistive circuits. So first we need to take one of the node as a reference. We take one of the node as a reference, and then with respect to that we will write the potentials of the different nodes. And if some of them are unknown for us, then we take some variables there. So where the potential is unknown for us, then there we take some variables like x, y, z, or you can consider, or v1, v2, v3 you may consider there. So then after that we write the just a nodal equation. Nodal equation is nothing but sigma q is equal to 0. That means the algebraic sum of all the charge at that junction should be equal to 0. So then by solving those equations you will get like you will get that values there. That means potential values you will get. From that you can calculate these values here. That means either potential differences you may calculate, or effective capacitance you may calculate, or charges at the different junctions you may calculate there, right? And so now let us say this for the same previous problem I am going to apply for this here, or just to mention that procedure generally for applying this nodal method, which we mentioned already for this, just briefly mention about that procedure. In nodal method, we take any one of the node as reference. Any one of the node as reference. A reference in the sense whose potential is taken to be 0. Whose potential is one of the node as taken as a reference. That is, one of the node is assumed to be grounded. One of the node is assumed to be grounded. With respect to that, we will write potentials of the different nodes. With respect to that, we will write the potentials of the different nodes by assuming some variables for the unknown nodes. By writing, assuming some unknowns for the assuming some variables for the unknown nodes. By applying nodal equation, or nodal equation is nothing but our KCL, Kirchhoff current law, or Kirchhoff first law at the unknown junctions or unknown nodes, and by solving those equations we can find the potentials. By solving those equations we can find the potentials of the unknown nodes, right? Now let us take our previous example only I am taking here. So here capacitance is like 2C. This is our circuit what we considered previously. This is 2C and this is C and this is 2C. And this is some point A here and this is some B. So now we need to assume that one of the node as a reference. So I am assuming that this node as a reference here. So that means we are assuming that this is connected to the ground. This node is connected to the ground. So it is zero potential here. And now actually here potential is not applied. We need to assume some potential here. So I am taking this as some V0. So V0 is the potential for this junction I am taking here. Now we need to write the potentials for the different junctions we need to write here, right? So then let us take this as some junction C and this is the junction D. Let us consider here. Now for the junction C you can't write the potential there, right? So then potential of the junction C you can't write here. So I am taking some variable here. Suppose I am taking this as VC, let us take here. And this is similarly for this junction I am taking it as VD here, the potential difference across that. So then that is the potential potentials of those junctions there. Now here two junctions are there for this unknown potential here. So we need to write the two nodal equations there. And so now let us write the two nodal equations for that. By nodal equation at node C. So now I am writing this nodal equation at the node C. So now let us write here. Just we know that node C is nothing but, nodal equation is nothing but sigma q is equal to 0. Right? And so now here this potential, the charge across this we can write this as sigma q is nothing but, here we can consider this as, this is suppose a plus and this is minus, and similarly this is plus and this is minus you may consider here. And this is and actually here we can write this another way is, while writing this Kirchhoff law here you can write either sum of the isolated charges is equal to 0 you can write, or otherwise we assume like higher potentials that when you are writing that node is considered to be a higher potential, like that method also you can find, you can follow here, alright. And so that just I am writing, I am taking that method here which we proceed for this, which we applied for this resistive circuits there. That node is taken to be either higher potential or lower potential. So here I am assuming that node has a higher potential. So right. So then charge flowing along this direction we can write this as Vc minus V0 into C. So Q is equal to CV formula. V is nothing but potential difference we need to write. Now along this direction if I apply Vc minus 0 into 2C along this direction. Next along this direction we need to write here plus Vc minus Vd into there also 2C. This is equal to 0. Just you can take, you can assume like current is flowing along this direction. Instead of current we need to write it as a charge. So that charge is nothing but potential difference into this capacitance we need to write here. And so now we can simplify this. Vc minus V0 plus 2Vc plus 2Vc minus 2Vd is equal to 0. And then you may write this expression for this, you may get one relation here like CVC, 3Vc and 5Vc. 5Vc minus 2Vd is equal to V0. Let's suppose this is equation 1. And then next similarly apply for this node D. So by nodal equation at node D. So here also this is nodal equation, by nodal equation at the node C. And so now you can write this as same process. Now we need to assume that D has higher potential. So that charge is flowing along this direction and along this direction and along this direction we need to assume there. So I can write this as Vd minus V0 along this direction into 2C plus, and along this direction Vd minus 0 into C. That is the potential difference between these 2 points. And next we need to write potential difference between these 2 points. Plus now we need to assume VD as a higher potential. So when you are writing for that junction only we need to assume as a higher potential there. And so now we can simplify this. So again you can write this as 2 into VD minus 2 into V0 plus VD plus 2 VD minus 2 VC is equal to 0. And so here I can write this equation as like minus 2 VC plus 5 VD is equal to 2 V0. This is equation 2. And now we need to solve that equation 1 and equation 2 here. By solving those equations you will get the expressions for VC and VD, so that you can assume that how much charge is stored or how much charge is flowing in these directions here. So now for this just what we can do is we can multiply this equation with the 2 and this equation with 5 and let us add them. So that means equation 1 into 2. So that this equation will becomes as we are multiplying this equation with the 2. So observe this. So then this value I can write here it as 10 VC minus this is 4 VD is equal to, we are multiplying with the 2, so 2 V0 you will get. And next equation 2 we are multiplying with 5. That means this is our equation 2, we are multiplying with 5. So it is minus 10 VC plus 25 VD. This is 10 V0 you will get. And now let us add these two equations here. And if I am adding those two equations, then this is 21 VD is equal to 12 V0. And therefore this VD is equal to 4 V0 by 7. So this is our VD value. And now by substituting that VD in either of these equation 1 or equation 2, you can find that VC expressions there. So therefore from equation 1 I can write this 5 VC is equal to V0 plus 2 VD. So 5 VC is equal to V0 plus 8 V0 by 7. That means after substituting this VD value there. And therefore this value we can write this as VC is equal to 7 plus 8. So 15 you will get. So I can write this as 3 V0 by 7. Is it clear? That means 7 plus 8 if you are taking that LCM. So which is say 15. So 15 and this 5 3 times will be cancelled. So you will get like that. So now that is V0 and VD and VC values there. So after getting this, simply what you can calculate here is, so now let us consider this charge flowing along this direction is Q1 and a charge flowing along this direction is Q2 and a charge entering the circuit is Q. So now we need to find this Q1, Q2 and Q values here, right? And so now let us write this equation here. Now Q1 value I can write here as Q1 is equal to C into now V0 minus VC, right? That VC value is 3 V0 by 7. So that means what we can write here it is 4 CV0 by 7. This is our Q1 value. And then Q2 value. Q2 value is nothing but charge stored on this capacitor which we are assuming flowing along this direction here. So that charge I can write here it as 2C into V0 minus VD. So VD value we already calculated there, minus 4 V0 by 7. So which is nothing but you can write this as 6 CV0 by 7, right? And so now you can find this total charge is nothing but, now I will write here the total charge flowing is nothing but Q1 plus Q2 we can write here. So the total charge Q is equal to Q1 plus Q2. That means this Q is the charge drawn from the cell, right? Q is the charge drawn from the cell here. Total, if you are assuming a cell is connected. So then let us add these two values here. So 4 CV naught by 7 plus 6 CV naught by 7. So Q is equal to, you can write this as 10 by 7 CV naught you can write. But this Q value we can write as, if C is the total effective, then we can write this as Q is equal to C effective into V naught we can write here. Is it clear? V naught is the potential difference applied between these 2 points we are taking here. If C effective is the effective capacitance, if you are replacing all these 5 capacitors by a 1 capacitor having that C effective capacitance, then total charge stored on that we can write as Q is equal to C effective into V naught we can write. And therefore you can substitute that C effective into V naught is equal to 10 by 7 C into V naught you can write here. Therefore that C effective is equal to 10 by 7 C you can write. So that is our effective capacitance for this circuit here by using this nodal method. So right, so that is our nodal method application here. You can take any node as a reference and we should follow that. And if actually numericals are there, then you can solve it easily. So I will take an example for this numericals here so that you can solve that problem easily. So as the capacitors, that means in resistors we already applied this nodal method. Just I will give some two problems here. So just to solve by nodal method there. So now let us see this problem based on the numericals. I am explaining one more problem here so that you will get more clarity about that and you may practice that problem there. So that means this is the given circuit here. In this circuit we need to calculate charge on all capacitors we need to calculate here, right? So this is 20 volts and here one more cell 10 volts is connected like this. So that means in this you can't identify the series and parallel combination of the capacitors directly, or you can't apply any symmetry methods also. That means only 3 capacitors are there, 1, 2 and 3, right? So you can't apply any of those. So one way is either you need to apply either Kirchhoff laws or you need to apply this nodal method only. So now we are applying this nodal method here. So I am taking this node as a reference. So as you wish, any node you can take as a reference. I am taking for example this as a reference here. So then if this is reference, then this is 0 and then this is 20 volts battery is there. So this point must be 20. And so then here we are assuming that we can't write the potential at this point, and so this point is this node I am naming it as A, and so this is VA. And then here if it is VA, then here potential drop 10 volts must be there, so it will be 10 plus VA you will get. And so this is 10 plus VA and same 10 plus VA will be there. So now we need to write the nodal equation at this node here. So then charge flowing along this direction, sigma Q is equal to 0 at this point. So charge flowing along this direction is nothing but charge flowing along this direction, VA minus 20 into this capacitance C1, which is 2. So that is nothing but this positive term here. Next we are writing charge flowing along this direction here. So VA minus VA value we need to assume it as a higher potential. So VA minus 0 into this 4, which is nothing but our second term here. And next here the important thing is, see here in this path here cell is there, here capacitor is not there, then capacitor is connected here. So then here just we need to write how much charge is stored on this or how much charge is flowing along this direction. That means actually how much charge is stored on that. So that means here no capacitor is there here. So but here this potential is 10 plus VA. So that potential difference we need to write here for this. So 10 plus VA, that charge is nothing but charge flowing in this path here. So is it clear? So for this, instead of taking this VA, potential difference across this capacitor we need to write, because no capacitor is there in this path here. So then 10 plus VA minus 0 into this 2, that is nothing but our third term here. By simplifying this, we are getting this VA value as 2.5. See, once this potential is known, then charges on C1, C2, C3 you can write like this. Charge on this capacitor is nothing but potential difference, 20 minus this 2.5 into this capacitance, that is 35 microcoulombs. And a charge on this capacitor you can write this as the potential difference. This is 2.5 and this is 0. So 2.5 minus 0 into 4, that gives 10 microcoulombs. And similarly charge on this capacitor, as I said, only this potential difference you need to take, 10 plus 2.5 minus 0. So that means 12.5 into 2, 25 microcoulombs you need to write here. That is the charge on this capacitor. And actually, if it is required, you can represent the polarities also. That means which plate is positive and which plate is negative, you can represent. This is higher potential, so this plate is positive, and here it is higher potential, so this plate is positive. And for this is higher potential, so this place is positive. Like that, you can identify the polarities also. Now similarly, solve the circuit here. That means same question, find the charge on all capacitors. There is our question, find the charge on all capacitors. Here these two are the cells here, and this is another cell, 20 volts. 3 cells are there, and then 4 capacitors are there. So find the charge on all capacitors, right? So practice that problem. That is a nodal analysis method here, right? So that means practice some more problems by using this nodal analysis here. So then because as we discussed this, all these methods in current electricity, I am not spending much time on this because some other models are there in the capacitors here, right? And so next in this infinite circuits will be there. I will explain that infinite circuits in the next class, right? Thank you.